Hey everybody and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy where we are learning networks together. And on this video, on part 4 of this series, what we're actually going to go through is more detail into EVPN and VXLAN routing. EVPN standing for Ethernet Virtual Private Network, VXLAN standing for Virtual Extensible Local Area Network. Two big protocols, two big acronyms working together to really bring a lot of power to data centers, enterprise and campus networks. Now, as I said, this is part 4 in this series. In part 1, what we did is we touched on the basics. We understood the key terms, the terminology, and really why EVPN and VXLAN is here. In part 2, we touched on more of the benefits of EVPN routing. EVPN is a huge protocol. It's actually a sub-protocol. It's a family within multi-protocol border gateway protocol, or MPBGP. And in part 3, what we did is we then started going into a little bit more detail into the different EVPN packet types. Specifically, we went into types 2 and 3. Type 2 being that Unicast, MAC or optional IP advertisement of a host, a device connected to a leaf, or it could be an access switch, and then advertising that learned MAC address throughout the entire EVI or the EVPN virtual instance, i.e. to all connected routers and switches that are connected to that same network. And the type 3 being for broadcast, unknown unicast and multicast traffic, or BUM traffic. We need the type 3 to manage and really replicate BUM traffic efficiently, and there was 2 different ways to go through that. So if you haven't seen these previous parts, please check them out. Highly recommend you do so before this part 4, where we're going to continue talking about the EVPN packet types, but specifically we're going to be talking about EVPN type 1 and EVPN type 4. Now, this is really all to do with ESI, or Ethernet Segment Identifier. It's one of those key terms that you do have to know before proceeding forward in this video. But you will learn the differences between the EVPN type 1 and the EVPN type 4. And actually, when we talk about the EVPN type 1, there are actually 2 different types of this type 1. Yep, you heard me right. I told you EVPN is a big protocol. So there's a route type 1 for the ESI, and there's a route type 1 for the EVI. I know, we'll get there, don't worry about it. And then we're going to move on to the EVPN route type 4, where we start talking about a designated forwarder and why we need a designated forwarder when there is an Ethernet Segment Identifier, or ESI, in the network. As always, if you like this video, if you like my content, please give me a thumbs up. It's the best way to support my channel. Other than that, let's just get going straight onto the theory. So you've probably noticed at this point that I've got here type 4 and not type 1. That is not a typo. There is a reason why I'm starting with the type 4 EVPN route type, which is called, from an RFC point of view, the Ethernet segment route. There is a logic to this. When we move on to the route type 1, the auto-discovery EVPN route type, you will need to know this first, because I'll be talking about a forwarder, designated forwarder, when we go on to route type 1. And if I haven't covered that first, you're going to be like, well, what's a designated forwarder? What's that all about? So it makes sense to go through what is a DF, what is the route type 4, and that paves the way very nicely to discussing and going through the EVPN route type 1. So, scenario. What we have here, as you can see, is we've got this server here, server 3, which is connected to both leaf 2 and to leaf 3. And of course, it's multi-homed. Multi-homed meaning it has a connection up to leaf 2 and of course across to leaf 3. Now, this Ethernet segment here, this is basically a link aggregation group. But in the EVPN world, we are calling this an Ethernet segment. Notice the link here, Ethernet segment, and that will have an identifier. So ESI, we are calling it an ESI. And EVPN does this very, very well via the route type 1. Leaf 2 and leaf 3 will advertise across to user 1 and all the other users connected to all the other leaves and VTEPs connected in the network, obviously in this diagram there's only 3 to keep things simple, leaf 2 will advertise over to leaf 1, and leaf 3 will advertise over to leaf 1 as well. Now if you want to get to this server, you can do so via leaf 2, and you can do so via leaf 3. And I'm just going to change the colour because it sort of blends in quite nicely, doesn't it? And here we go, here's my favourite colour, bit of blue there for you, dashed a little bit of purple. But at this point, leaf 2 and leaf 3 have advertised over to leaf 1 that if you want to get to this server, you could do so via spine 1, you could do so via spine 2, and therefore leaf 1 has multi-paths or multiple ways to get to this server. So if user 1 sends in a packet, let's just go with a Unicast packet right now, and let's just say it's going to go via spine 1. The Unicast packet is of course destined for the server, and we're going via spine 1. The Unicast packet goes up to spine 1. Spine 1 then sends it to one of these leaves, either leaf 2 or leaf 3. Let's just say it goes to leaf 2, just for example. At this point here, leaf 2 will forward that down to the server, and then that's done. Mission accomplished. But that's a Unicast packet. What happens when there's a broadcast packet or a unknown Unicast or multicast packet? Then things get a little bit more interesting. So user 1 sends in a bum packet into leaf 1, and again it is destined for this server. Now at this point here, leaf 1 knows that it can get to this server via spine 1, via spine 2, but also it knows it could get to the server via leaf 2 and leaf 3. Okay, now because this is a broadcast, unknown, unicast and multicast packet, what's it going to do? It's going to send it up to spine 1. It's also going to send it across to spine 2. It's then, via the spine, is going to be sent down to leaf 2, down from spine 2 to leaf 2, from spine 1 to leaf 3, and from spine 2 down to leaf 3. Almost got my numbers confused there. I know I've done that a few times in these videos, but you get the idea. Suddenly there's this massive broadcast, because it's bum traffic at the end of the day, going throughout the network. And here leaf 2 will see, this is a bum packet destined for this server. This server is attached to me, is connected to me on whatever port's connected here, and it's going to forward that packet down to the server. But guess what? Leaf 3 on that VTEP has also received that bum packet, can see that this server is connected to me, and it will then forward that packet, that bum packet, down to the server. And at that point, the server has received duplicate copies of the same packet. That's not good. But what happens when the server sends in a bum packet to either one of these leaves? So let's say the bum packet comes up to leaf 3. And I'm just going to write here, bum, for broadcast, unknown, unicast and multicast traffic. I'm a bit of a child. I always have a little giggle inside when I say that. But moving on. So the bum traffic has come up to leaf 3. And the VTEP here can see that, I have got interested parties in VNI 5010, VLAN 10 at the end of the day, and I've got interested parties over on leaf 2 and over on leaf 1. So via spine 1 or spine 2, doesn't really matter, but let's just say via spine 2, it forwards those bum traffics via spine 2 over to spine 1. No problem there whatsoever. But what happens when it sends those bum packets through spine 2 down to leaf 2? Well, when those packets go to user 2, who's in that same VNI, in that same VLAN, that's fine, that's no problem. But leaf 2 will also then forward that bum packet back to the server. You see what's happened here? We have created a loop. These packets will just keep going round and round and round and round. You've got a routing loop there. That is never a good thing. So we need a way to actually stop this from happening. We need a way to break that loop and to stop all these packets being sent from outside of this ESI, to stop those duplicate packets actually being received, as well as those routing issues. And this is where the concept of the designated forwarder comes into it, because what will happen via this type 4, type 4 is all about electing a designated forwarder for an Ethernet segment at the end of the day. It's all about Ethernet segments. We are going to elect one of these as a designated forwarder, and the other leaf, the other VTEP that is connected to that same multi-homed device, will be a non-designated forwarder. So I'm just going to put NF here. So let's use that example again, and let's just do it in a different color. Let's do it in red. Let's say again that user 1 has sent in bum traffic up to the leaf, and let's say it's just going to go via spine 1. So just for example, so the bum packets come up to spine 1, and then of course, because there's multiple paths to the same destination, spine 1 will send that packet down to leaf 3, and it will still send it down to leaf 2. But at this point here, the non-designated forwarder will see, hang on, I am the non-designated forwarder for this VNI. Therefore, what am I going to do with this packet? I'm going to drop it. I'm just going to immediately discard it, and therefore it's not going to go onto the server via me. But the designated forwarder, upon receiving that bum traffic, will know that this server is connected to the same, or is connected to a Ethernet segment that is connected to me, and it's got this identifier, whatever that identifier actually is, and then it will send on that bum traffic to that server. Great, so we've stopped duplicate packets from being received. But what happens when the server sends bum traffic? Now, it's at the end of the day, the server, and just like any host, it's going to do some kind of hashing algorithm. It's going to decide in which direction to send that bum traffic. Now, it could go up to the non-designated forwarder, or it could go up to the designated forwarder. At the end of the day, we want that because this is an Ethernet segment. It's not only allowing resiliency, but it's allowing load balancing for that server. So we don't want to stop that. So let's say the packets come up to leaf 2, which is that non-designated forwarder. Now this is where there's a little bit of overlap with the route type 1. We're going to go through it next, but this is the auto discovery, and I don't want to steal too much too soon in terms of the information. But there's a bit that what leaf 2, the VTEP, will do is it will flip a bit, and as that broadcast on Unicast and Multicast traffic goes over to leaf 1 and comes back to leaf 3, the actual designated forwarder, the designated forwarder will see, hang on, this bit has been flipped and I'm not going to send that bum traffic back into this Ethernet segment. I'm not going to do that. So in this way, the non-forwarder actually becomes a designated forwarder. And if that server sends the packet, that bum packet, up to leaf 3, that's not an issue because this is the designated forwarder. It will forward it over to leaf 1. It will not forward it over to the leaf 2 because this is the non-designated forwarder, and it knows this because these two leaves in this particular case, they're actually monitoring each other. They're monitoring each other for health to make sure they're still there, still alive, and they are negotiating between themselves initially when this Ethernet segment is built, which is where the route type 1 comes in. They are negotiating between themselves using this type 4 which one of these leaves will be the designated forwarder and which one of these leaves will be the non-designated forwarder. And this is where we start to get into a bit more information now into the EVPN route type for the packet header itself. So what do we have in this route type 4? Well, of course, we've always got that network layer reachability information, i.e. all the prefixes that can be reached that are being advertised in this update message. Then we obviously are going to have a route distinguisher. Just like we've gone through on previous videos, this will be a type 1. If you don't know what that is, please refer to the previous videos. But just very quickly, it's going to have the router ID. So this would be the router ID of leaf 3. And then it's going to have another number. Typically, always that's going to be the VLAN, or in this case, the VNI as well. So that the receiving devices, whether it be leaf 2 or leaf 1, can see, it's come from leaf 3 and it's for this particular VNI. Of course, we're going to have the next hop IP address. So the next hop being the loopback 0.10 for leaf 3. I'm saying .10 because at the end of the day, this is for VLAN 10. It's for VNI 5010. So whatever's configured for the loopback 0.10 on the leaf will be the next hop IP address to get to this particular ESI, which has been advertised by both leaf 2 and leaf 3. And that actually brings me on to the next part, which is the ESI itself. Now, interestingly, I've recently read that the ESI isn't just a random number a random 10 hex number. It actually has a meaning to it. Now, there's different ways that I've read that it can be defined, but what it's typically doing is taking the MAC address of the actual originator of, in this case, the server itself. So let's say here the MAC address, just for example, is aa.bb.cc:11:22:33, just for example. At that point, the MAC address, or sorry, the ESI would be something like 01. It's got to start with a 01, and then it's going to be aa.bb:11:11. You get the idea, 22:33. That in itself is great because leaf 1 at this point can see, and you're going to have additional values here to get to this 10 hex number, but at this point leaf 1 can see, there's multiple paths to get to the ESI. It doesn't know at this point what the MAC address is of the server because that's where the route type 2 comes into it, but it can see that there's an ESI contained within this route type 4, and actually here is the MAC address configured within that ESI value itself. But the main importance here is when it comes to establishing that designated forwarder between leaf 2 and leaf 3. And just very quickly, you're also going to have a virtual network identifier or VXLAN network identifier, but when we know that's going to be 5010, 5010, 5010, that's straightforward. But let's move on with this ESI, because what there is, and this is where the route type 4 distinguishes itself from the other EVPN route types, is we have these extended communities in these EVPN route types, because EVPN is a family, it's a protocol that sits within multi-protocol BGP. And these extended communities would typically define a route target in the EVPN world. We are still defining a route target, but for the EVPN route type 4, this is, and it's automatically configured to be an ES import route target. What on earth does that actually mean in English? Well, what this means is that leaf 2 and leaf 3, they are connected to this server via this multihomed address, via this multihomed connection, sorry. And they can see the MAC address of this server, of course, via this ESI. And then they're configuring that ESI to be a 01: with the MAC address of that server. And then they're advertising via this route type 4, they're advertising that ESI throughout the network. So leaf 3 will advertise it to leaf 1, leaf 2 will advertise it to leaf 1, leaf 2 will advertise it to leaf 3, and leaf 3 will advertise it to leaf 2. But because of this ES import, the leaf 1 is going to receive that update message and see, yep, it's got these network layer reachability information, it's got this route distinguisher, the next hop, this ESI, this for this VNI, but oh, hang on, there's this ESI import here, and I don't have that because I do not have an Ethernet segment connected to me. I don't have this extended community defined, which is taking that Ethernet segment identifier and applying that within a route target. It's actually something that's just created by default within the route type 4. And so all other devices which don't have that same ESI connected to them, they're not going to have this hidden policy. They're not going to have this hidden policy that defines if you receive this ESI import via this route type 4 and it has this value, just drop it basically. At this point, leaf 1, when it receives these route type 4s via leaf 3 and from leaf 2, or in vice versa there, it's just going to drop those packets because it's going to see, I don't have a multi-armed connection over to the server. I don't know what that ESI is. I haven't created that hidden policy that allows me to import this route type 4. So it's just going to drop it. So therefore, leaf 1 will not become part of this process of being either designated forwarder or non-designated forwarder. But obviously leaf 2 and leaf 3 are part of this Ethernet segment, and they both have got that same Ethernet segment identifier. So you're going to have an ESI here and an ESI here. It's going to be identical, so it's going to have the same Ethernet segment identifier in the route type 4, which is then within the extended communities and thus the ES import policy will be the same. And then they can basically see, hang on, Leaf 2, you've got this ES import policy for the same Ethernet segment identifier. Leaf 2 is going to say to Leaf 3, you've also got the same ES import policy for the same Ethernet segment identifier. And by the way, this can be on a per VNI basis. So this will change per VNI. That's why it's actually defined here. So if you've got 5020 as well, you're going to have different route type 4s per VNI, and they're going to identify the ESI that it sits behind and this ES import policy. But because of this now, we can now start the DF, the designated forwarder, or the non-designated forwarder election process. But how does it actually decide on who's going to be that designated forwarder? Well, it's all based on the originator IP address. There'll be an algorithm to decide who gets the DF election process. It's either going to be higher IP or lower IP. I haven't gone into that level of detail, so I wouldn't want to assume. Obviously, it will change. But just know that the decision-making process is based on the originator IP address, higher or lower. And this does it in a round-robin distribution. So in a round-robin basis. So as I said, you might have 5020 here. So the Leaf 3 might be the designated forwarder for VNI 5010, but for VNI 5020, if that's also on this server as well, or configured on the leaves to be part of the server, I should say, then you could have Leaf 2 being the designated forwarder for 5020. And at which case, for 5020, Leaf 3 will be the non-designated forwarder. And guess what? For 5010, Leaf 2 will be the non-designated forwarder. That is essentially the purpose of the route type 4, is it's allowing us to define who is going to be the designated forwarder, who is going to be the non-designated forwarder. And this is done, as I said, on a per VNI basis, really on a per VLAN basis, because we map a VLAN to a VXLAN network identifier, to a virtual network identifier at the end of the day. And these devices are constantly monitoring each other. So if Leaf 2 just fails, or this connection fails, or the link goes down to the spines, whatever it is, then obviously at this point this might no longer be multi-homed, but then Leaf 3 would become a designated forwarder for all the VNIs, and that's where a type 1 actually comes into it, which we're going to go on to shortly, the subject called a mass withdrawal. We'll come on to that shortly. And remember that for this type 4, there is this ES import route target, and that is hidden and automatically created for you by the devices, by the leads, in this case, that are connected to that same device. They'll have that same Ethernet segment identifier for that particular VNI, and that would be defined in that ES import policy. And obviously in here would be that MAC address. It could also be the IP address. I've read some documentation, but for me, EVPN being that layer 2 at the end of the day, it makes sense to have the MAC address of that device, of that server contained within that ESI. And because Leaf 1 doesn't know anything about this server in terms of the MAC address within this route type 4, it's got no connection to it, it's just going to drop those policies, drop these route type 4s when it gets received. But because Leaf 2 and Leaf 3 have connections to this server in a multi-homed connection, have this ESI, know the identifier of that Ethernet segment, they create the same ES import policy, and when that's advertised to and from each other, they will then start that designated forwarder, non-designated forwarder election process, tongue twister there. And then that will really improve the performance when bump traffic is sent, either from a device that sits outside of this multi-homed environment, or even from inside that multi-homed environment. So let's now go through the EVPN Route Type 1, which is called the Auto Discovery. The name is quite good actually, because what it does is it allows remote leaves to learn if you want to get to a given destination via the VPN tunnels, because don't forget everything is going to be over the VPN tunnels. That's my drawing for VPN tunnel. I do apologize. But it allows these leaf devices to learn remotely that if you want to get to this multi-homed device, the server in this case, you can get to it via two different VXLAN tunnels. You can do it to leaf 2 or you can get to it via leaf 3 itself, i.e. it's auto discovery. And there's actually two different types of type 1 messages, of type 1 updates. So we've got a type 1 message for an Ethernet segment identifier, but there's also a type 1 message for the Ethernet or EVPN, virtual instance. Okay, we're going to go through this one at a time, of course, but you should also know, just from a high level, that the ESI provides two functions. It allows for mass withdrawal, also known as fast convergence, as well as a split horizon rule, which I did sort of almost touch on when it came to the route type 4 message that we just went through. I touched on it ever so slightly. So we've got a split horizon rule here, which is, guess what, for the broadcast, unknown unicast and multicast traffic. I did touch on it ever so slightly, like I said. And then we've got this EVPN virtual instance route type 1, which is for aliasing. So we'll go through this one at a time. But first, let's actually go through this ESI, this Ethernet segment identifier. So as we know, this server here, it's multi-homed. It's got two connections to the leaves, one each. Obviously, we've got a connection up to leaf 2 and a connection up to leaf 3. Now, from the server's point of view, this is just a link aggregation group. It doesn't see it as anything differently, and it will be running, LAGP, link aggregation control protocol, to manage this. But the ESI is advertised from the leaves up. So the leaf 2 will advertise over to leaf 1 and leaf 3 will advertise over to leaf 1. This particular Ethernet segment identifier, i.e. the lag itself to get to the server. And as we know, this is a 10 hex value, which is recommended. I've seen a lot of documents on this, to have the MAC address of that server contained, or of that client contained within that ESI value. And what I want to go through first is actually that split horizon rule, because I did touch on it ever so slightly in the last part. And to touch on that, we need to first go through the contents of the route type 1 header, all the headers, the information that you get inside this update message. Well, just like any other update message for EVPN, you can have the network layer reachability information, which, guess what, defines the prefixes. And I didn't say it on the last one, but of course they are also going to be path attributes in there, same as in the route type 4, local preference, origin, AS path, router ID, etc, etc. There's lots of information that's contained within these path attributes. And of course, we're going to have that route distinguisher. I'm not going to go through it again, but it will be a type 1 that identifies uniquely who has advertised this update message, who has it come from, and the VNI in the EVPN-VXLAN world, the VNI behind it. And we are then going to have an Ethernet segment identifier in this type 1. Now, because the server here is multi-homed, it's got two connections, it's got redundancy and also load balancing. As we know, as I just said, this is going to be a 10 hex value. It must not be all zeros. If it's all zeros, it means the server would only have one connection. If it's a multi-homed site, if it's a multi-homed device, or even another networking device, it has to be a non-zero. We are going to have a next hop, which would be the leaf's loopback 0 address, and that in this case that would be a loopback 0.10 for VLAN 10, VNI 5010. And I'm just going to write it down here just to get a bit of space, but then we're then going to have again these extended communities, and it's really these communities that give the difference between these EVPN route types. And for these extended communities in the EVPN route type 1 world, this is going to be called the ESI, Ethernet segment identifier, label, and guess what? Extended communities. I'm not going to write it all out, but you get the idea. And within here, there's quite a few bits. So there is a split horizon bit. So it's only one bit, which could be a 0 or a 1. So two different options. Now, if you recall back to my previous parts where we went through the route type 4, I gave the scenario of when the server sends up a bump packet to leaf 2, and leaf 2 was a non-designated forwarder, at which point it would then send via the VTEP tunnels that bum traffic to all interested devices, to all remote leaves that have VNI 5010. So it would send that bum traffic to leaf 1, and it would also send it over to leaf 3, which was that designated forwarder. But then I said that leaf 3 would drop that packet. How would it know to drop that packet? It's because in the route type 1, it has flipped this split horizon bit. So at this point, leaf 3 learns that this has come from the non-designated forwarder, and it's connected to the same Ethernet segment identifier as me, and therefore I need to drop this packet. I need to drop this bum packet or packets. That is how leaf 3 knew not to forward that bum traffic back to the server in the first place. Pretty smart. Two different route types. Route type 4 allowed the designated forwarder to be elected and the non-designated forwarder, but still allowed from inside the ESI that server to send traffic, bum traffic up to leaf 2 to forward it, but if it came back to the designated forwarder through EVPN Route Type 1, the ESI, EVPN Route Type 1, for that designated forwarder to then drop that packet. Pretty smart. So we've gone through the split horizon, and as I said, that is for bum traffic. What there is also in here is what's called a single flag. It's a single bit. And again, that can be a 0 or a 1, so two different options. Now in this case, this would actually be coming from both leaf 2 and from leaf 3 when they advertise it over, just for example, over to leaf 1 via the VTEP tunnels. Now if it's set to a 0, it means active, active. What that means is that leaf 1 has learned that if you want to get to this destination server 3, you can use both of these connections. You can use the connection from leaf 2 to the server, but you can also use the connection from leaf 3 to the server. Really, in the Juniper Junos world, we have active, active at the time of me doing this on the QFX devices. Please read documentation. It might have changed, obviously, in the future. Upon me doing this video, it's active, active. If it's set to a 1, and I'm just going to write it over here, that means it's active standby. Active standby means that only one of these links would be used for forwarding. So maybe the connection between leaf 3 and the server is not used, and only the connection between leaf 2 to the server is actually used. And I also said in the ESI EVPN route type that we have this mass withdrawal function for fast convergence. What this allows is if this connection goes down between leaf 2 to the server, leaf 2 would send out an EVPN Route Type 1, an ESI EVPN Route Type 1 to all other leaves connected, and even over to leaf 3 and all other connected leaves, spines, etc. in the network. And it basically withdraws all previous Route Type 1s that have been learned over the link. So on this link here to the server, yeah, I've kept it simple. There's only, as I said, one MAC address. But if there's a server, it's going to have hundreds or thousands of virtual machines potentially in there, depending on size, etc. I know. But needless to say, a lot of learned addresses. And using that route type 1, we can now withdraw, when this link goes down, all those learned MAC addresses and withdraw them as an advertisement to leaf 1 and to leaf 3 and to all other devices, basically notifying them via this update message, do not use me anymore to get to this destination or destinations because for whatever reason the link has gone down. And moving on to the EVI, now the EVPN virtual instance, what this allows is aliasing. I have covered this a little bit on a previous video, and to be honest, there's not really much to say about this feature that's delivered via route type 1. But what we do know is that when leaf 3 and leaf 2 are connected to this multi-homed server, one of them is going to learn that MAC address, and via the route type 2, that MAC address is then going to be advertised over the network. So say user 1 wants to get to this server, and leaf 1 will send that traffic via the VTEP, and it learns of that server's MAC address via that route type 2 that's being received via leaf 3. But we don't want all traffic to keep going to leaf 3 because at some point it's going to get overwhelmed potentially with traffic. And this is where the route type 1 EVI comes into it. So leaf 2 would advertise over to leaf 1, a route type 1 EVI, and so would leaf 3 would advertise over to leaf 1, a identical ESI, EVI to leaf 1. And within here is that Ethernet segment identifier, identifying that link aggregation group that's between leaf 2 and leaf 3. And again, it is going to be identical. Now, at this point, leaf 1 has only got a route type 2 from leaf 3, but it's got a route type 1 containing that ESI value from leaf 2 and from leaf 3. And therefore, it knows that this MAC address of the server, or all the MAC addresses of that server that sit behind this multi-homed connection, can get to it via leaf 2 and via leaf 3. So even though it's only got one route type 2 for a MAC address from leaf 3, because that ESI is the same and it's been received from leaf 2 and leaf 3, it can then send traffic to that same destination over multiple paths. It's what's called aliasing. There we go. That's what it is. So everybody, that's the end of this video. It's the end of part 4 where we've gone into a lot more detail into the route type 4 and the route type 1. And really they work hand in hand with each other. Just like in the previous video, part 3, where I said with the route type 2, you're going to get a route type 3. In this part, in this video, we've seen that when you have a route type 4 that works in conjunction with the route type 1. Route type 1 is all about advertising at the end of the day an Ethernet segment with an identifier throughout a network, i.e. it's multi-homed. And because it's multi-homed, you need that designated forwarder. You need that non-designated forwarder. That's where the type 4 comes into it. So a lot of information on these two EVPN route types. As always, I hope you found this video, this content useful. If you did, please give me a thumbs up. It's the best way to support the channel. Any questions or comments, let me know down in the comments box. The feedback is always greatly appreciated. Other than that, thanks for watching. Goodbye.